In this video, we will introduce the idea of a span of a set of vectors. And the good thing is this idea is closely related to the idea of linear combinations. In fact, the span of a set of vectors is the set of all possible linear combinations of those vectors, right? So let's write down our definition and then take a look, a little deeper look at what this idea entails. So let's say we have a set of vectors. I'm going to call that set S, and here are my vectors v1, v2, vm, right? And where each of the vectors is a vector in Rn, right? So our n-dimensional Euclidean space, right? The span of S, right? So the span of S is the set of all possible linear combinations right, of these m vectors, right? So v1, v2, vm, right? And that's basically what a span is now we're looking at all the possible linear combinations of these vectors, and that gives rise to another set. So here's the notation that we use for span. The word is short enough that we don't abbreviate it. It's either the uppercase S span, like this, or sometimes you'll see the lowercase s span, like that. And this is a set, right? So if I'm spanning these m vectors, what it means is I'm forming a new set that consists of all the possible linear combinations of these m vectors. So now we'll have C1 times V1 plus C2 times V2 plus plus Cm times Vm, where all these scalars could be any real number. So the Ci's are real numbers, right? And that's what the span is. Now, as far as something interesting, and I'll just make a note of this. This set here is a finite set. It consists of only m elements, right? So this is an example of a finite set. It has only m elements in it, right? So it's a finite set having only m elements. But once we span them, right? And by spanning, again, we're allowed to do those two basic vector operations, scalar multiplication and addition. When we span these m vectors, we end up getting infinitely many vectors, because now we can choose any real number as our scalar for each of these vectors. So this set now is an infinite set, right? So we start with a finite set of elements, and through all possible combinations, we generate something that's now infinite, right? So we go from the finite to the infinite. Now, before we look at some algebraic consequences of this, I just want to sketch a couple vectors and their span so you can see what this all entails, right? So I'm just going to do a couple examples in R2. So we're going to work in R2. Why R2? Because it's easy to visualize, right? So suppose my set just consists of one vector. So let's say my S just consists of the vector v. And I'm not even going to like write down an actual vector. I'm just saying there's a single vector in my set, right? So let me sketch R2. And then let me sketch my vector v, and I'll just sketch it with the initial point at the origin. So wherever I want it to be oriented, maybe I want it to be oriented this way. So this is the vector v. Well, you know, by definition, if I were to write down the span of S, well, since there is just one vector, right, so there's nothing for me to add it to, but I do have the freedom of scaling it by, you know, any constant. So this would be CV, again, where C can be any real number. I'm not using the subscript simply because there's only one constant here, so I don't need to distinguish it between any other constants. So that's why I'm not using the subscript. But yeah, this is the span. So what would it mean geometrically? Well, I think by now we know what it means, or geometrically what happens to a vector when we multiply it by a constant. If that constant is positive and greater than 1, then it's going to take this vector and extend it indefinitely in that direction, right? And then if that constant is negative, right, then it's going to extend it in the opposite direction. So actually, the span of a single vector in R2 is just a line, right? So it's a line, right? So geometrically, so the span of a single vector, and this is actually true in any dimension, 2 or 20. If you're spanning just a single vector, what you get is a line. So it is a line, right? Pretty simple. Now, what if we have two vectors? Well, there are two possibilities in R2, right? So again, I'll do both of them. So let's say I have now U and V. Well, in terms of these two vectors, if I am asked to sketch these two vectors, there's really just one of two possible ways I could do it. One way is this. For instance, this could be my V, and then this could be my U, right? So essentially, they're already scalar multiples of each other. So then the span of these two, let's write it over here. So the span of this set, again, by definition, it's any scalar multiple of U plus any scalar multiple of V. Oh, I almost read my little harpoon there. So any scalar multiple of U plus any scalar multiple of V. Again, and we can use any scalars we want, right? So when we span U and V here, again, for instance, just think about the span of V. Well, again, that would be a line. And if we span just U, that will be the same line. And because they're already forming, or the vectors are already collinear, they lie on the same line, when we span them, we just get the same line. Right? So in fact, let me go ahead and indicate that this is a line. So even though I put an arrow on here, it's not finite like a vector, right? It goes on indefinitely, right? Similarly for this one, this is now a line, right? So if the two vectors are already scalar multiples of each other, then their span will still just be a line, right? So if, and I'll say it this way, if the vectors u and v are collinear, then the span of u and v is again a line. All right, so it seems like there are multiple ways we can generate a line, either using just a single vector or two vectors that are already either, acting in the same direction, right, or opposite directions. Once we generate that span, we're going to get all the vectors that lie on the line, right? So it's not just, the thing is, and maybe I should clarify this sketch, it's all these vectors. So a vector here, and then a vector here, and a vector here, right? So all the vectors that point in that direction with any arbitrary magnitude, and the magnitude is arbitrary because, yeah, we're allowed to scale them with any constant we want, right? So that's a second possibility in R2. The other possibility now, which is really the interesting one, is what if u and v are not collinear, right? So let's say, so another possibility is this, two vectors, but now here are my two vectors. Let's say that this is u, and let's say this is v, right? Well, the span is the same thing. Algebraically, this would be exactly what I would write down. It's the same span. It's the same set that we would generate. Or let me say it this way, we would generate the span in the same way. But the results are going to be different. It's not going to be a line. In fact, if you think about it, you might be able to see what's going to happen. All right? So just to give you an idea, let's say my scalars are 1 and 1, right? So for instance, if I wanted to visualize the sum of these two vectors, one way to do it is to take the vector v and put its initial point at the terminal point of u. So if I place my a point here and then draw the equivalent vector of v, but starting at this point, and do this, and technically I could do the same thing here, and then take this vector u, but now draw it with a initial point at the terminal point of v. So there's another copy of u. Well, if I think about it geometrically, going from this point to this point is the same as going one copy of u plus another copy of v. So if I just sketch this vector here, that green vector is u plus v, right? So I get a vector now that's not pointing in the same direction as u and v, so it's pointing somewhere else, right? And then think about it. If I were to then maybe take a half of u and then add v, so what would happen is if I take the half of u, then I would go here, and then when I add v, I would end up here, right? So by taking different scalar multiples of my two non-collinear, or yeah, I don't want to say non-linear, but not collinear vectors, once I do that, what I'll end up getting is lots of vectors. Let's say first all of these, and then all of these, and then again all the combinations now. So vectors over here, vectors over here, vectors over here, some short ones, some really long ones. So what I end up getting is not just a line anymore, but I get the entire plane. I get the entire XY plane, right? By simply taking any, uh, or I should say every possible scalar multiple of u and every possible scalar multiple of v, and then combine them, right? Form these linear combinations. I'm able to generate not just a line anymore, but the entire plane, right? So if u and v are not collinear, right? And I'm referring to vectors in R2 here, so are not collinear, then these two vectors span the entire xy plane. So they span R2. Pretty interesting, right? And when you think about it, if I'm limited in R2, this pretty much covers all the basic ideas. In other words, if I just have one vector, right, then there's no way for me to span everything. I'm just going to generate that line. If I have two vectors that already lie on the same line, if I extend them indefinitely, right, then again, all I'm going to generate is that line. But, however, if they happen to be pointing in different directions, right? So if by themselves they generate different lines, then when I span them, it's like it essentially now get all the possible lines, hence all the points or all the vectors in R2 are generated just by these two vectors, right? Pretty interesting, I would think, sort of geometric way of looking at the span. But the thing about the geometric way of thinking about it is that it is limited, right? Because as far as what we perceive geometrically, we can see and perceive things very well in 2 and 3 dimensions. But what about vectors in R4, R5, and so forth? You know, what do those spans look like, right? Well, that's where the algebra takes over and the geometry kind of fails. All right. So now let's look at a couple algebraic examples. Right. So here's an example, and let S be this set. So now we're going to look at a couple vectors in R3. Right. So there's one vector. And then here is another vector, right? And then so part A, I'm going to ask this question: is this third vector 0, 2, 2, is that vector an element in the span of S? Right? So they were using our, nice set notation, right? So is this vector in the span of S, right? Well, let's translate this to an algebraic problem. Right now, I'm getting stuck on geometry. Let's turn this into an algebraic problem, because again, even though we can sketch this, and after we do the algebraic solution, I'll give you kind of a sketch so that you can somewhat visualize what's going on. It might not be a completely accurate sketch, but it will be representative of what the solution indicates, right? So again, the question is now, is this vector in the span? So let's retranslate this question. So are there scalars C1, C2 such that if I take C1 times my vector 2, negative 1, 1, and then add to that C2 times my vector 1, 0, negative 1, is it possible to get the vector 0, 2, 2? All right. Well, let's see. Let's write this in our augmented form because we know this vector equation has several equivalent forms. There is the standard linear system, there's the augmented form, there is the matrix form, and then now there is the vector form. And I think the key is that we have to be comfortable moving back and forth between all those, or I should say amongst all those forms. So let's go to our augmented form because that I think still is the most effective, efficient way of solving systems. Also, we couldn't really use the matrix approach here, right? Because for instance, the coefficient matrix would be a 3 by 2 matrix, so we can't really talk about an inverse there, right? So as powerful as the matrix equation is, it is limited. But again, due to the even greater power of Gaussian elimination, then we can handle systems with any number of equations and any number of variables. So let's put this in at least an echelon form and see if we get a solution. Because if we do, then it means, yeah, our vector 0, 2, 2 is in the span of these two vectors. So, I mean, the system is relatively simple, but we have a 1 here. I'm going to go ahead and do a row swap. So let's swap the first and third rows. So we get 1, -1, 2. And then the second row stays the same. And then the third row is now 2, 1, 0. So now let's use that 1 as our pivot and eliminate the -1, eliminate the +2. So if we take, just take row 1, add it to row 2, and then -2 row 1 added to row 3, that produces my equivalent augmented form. So first row stays the same, and now we have 0, -1, and 4. And then here we have 0, 3, and -4, right? Well, I think you see what's going to happen here, right? Well, and if you don't, well, let's see. So again, to get a 1 in this position, let's say I take -1 times row 2. And I get this vector 0, 1, -4, and then 0, 3, -4. And if I eliminate the 3, I am not going to eliminate the -4. So let's do this here. So if I take -3 times row 2 added to row 3, then we get a 1, -1, and then 2. That stays the same. So, I mean, if for some reason we could have just ignored the third row, then we would have been fine. But no, we can't ignore it because it's given, well, it's requiring us to satisfy a certain constraint. But it seems like these two vectors can't generate this given vector. So we'll have 0 there, 0 there, and then we'll have 12, and then -4. So what's that? 8. Yep. So the thing is, this is a big red flag, right? So this tells me that our system is inconsistent. So we have an inconsistent system. Right? But we weren't asked about the system. We were asked something a little bit deeper. We were asked about the span. So what we can say, let me scroll over just a little bit more, that our vector 0, 2, 2 is not an element in the span of these two vectors. So this implies that the vector 0, 2, 2 is not an element in the span of, or let me write it like this. Right, so no matter what scalars I use, I wouldn't be able to start with these two vectors, the 2, -1, 1, and the 1, 0, 1, right? And generate this one, right? So in some sense, you can almost think of this as a target. You know, you're trying to create or you're trying to hit this target. And our darts happen to be any linear combinations, right? Or all the possible linear combinations of these two vectors. But no matter which ones we try, we keep missing the target, right? We can never get the 2 to 0, right? Now, so what does this mean geometrically? Well, when we did the two-dimensional sketch, we realized that when we span, so these two vectors, right, the -1, I'm sorry, the 1, -1, 2, and the -1, 0, 1, these are clearly not scalar multiples of each other, right? Because there's no constant that I could know, even if I tried to say, okay, yep, if I multiply the first, this vector by 0, I would still not get this vector, right? So notice that these are not scalar multiples, right? In fact, let's write that down. So 1, -1, 2 is not a scalar multiple of -1, 0, 1. Well, what does that mean? It means then, if I were to sketch these two vectors, right, and these are three-dimensional vectors, but I'm not going to do my three-dimensional coordinate system. Just imagine that they're in space here, right? But it just happens to be a flattened version of space. But the key thing is, if I take these two vectors and have them with the same initial point, because they're not scalar multiples of each other, they are going to point in different directions. And we saw what happened in R2, that if we have two vectors that are not collinear, then when we span them, we end up getting an entire plane, right? So if I span these, and I'm just going to sketch a portion of this, right? So if I span this, again, you know, I'll do that little kind of parallelogram thing. And then let's, right? So the red there is the span of these two vectors, right? So what does it mean that this third vector, the 0, 2, 2, is not in the red? Well, what it means now, because I'm in 3 dimensions, there's another direction that the vector could be pointing in. So let's say I take this vector and I draw this vector with an initial point somewhere in the red, anywhere in the red, then what will happen is this vector will not stay in the red. It's going to point somewhere else. So maybe it's pointing this way, right? And that's what it means geometrically if I span two vectors, let's say in R3, or technically any dimension, right? If I span two vectors, and if I find that a third vector is not in that span, it means that it's pointing, again, if I put the initial point somewhere in the plane, the vector is not going to stay in the plane. So it's not going to be like parallel to the plane. It's going to be somewhere else, right? So it could be like that, or it could be like that, or it could be like this, right? But it's pointing sort of in a third direction, right? There's this other direction in which the vector is pointing that is not spanned by the two given vectors, right? Okay, so that's again kind of a geometric way that we can visualize what's going on, right? Well, what if we had a different vector? So let's ask, so here's a part B to this question. So part B, and just as a reminder, these are the two vectors that we're trying to span. Oh, actually, well, yeah, we could try this. So part B is this vector. So let's say 5, -2, 3. So is this vector in the span of those two, right? The span of S, right? Well, let's do the same thing. Let's set up our columns, right? So actually, let me scroll back up just to make sure that we're using. Okay, that's what I thought. I forgot a -1 right here. Yeah, that should be -1. There we go. So those are our two vectors. So let me change this one. All right. And then let's say 1, -1, 2. All right, so let's try that one. Yeah, just want to make sure that it's consistent because when I wrote this down, I said that looks a little bit different. All right. So to answer this question, let's go and set up our augmented system. So my columns are the same, but now I have a different target vector, right? So there's a different vector that I want to produce. So it's 2, -1, 1, 1, 0, -1. And then we're going to augment it now with 1, -1, 2. Right? And let's see if we can get a solution out of this. Well, we can pretty much do the same set of operations, right? Because you notice our coefficient matrix here say is the same. It's the same A, so we can still do our row swap, right? So do our row swap, and we have 1, -1, 2, and then -1, 0, -1. And then 2, 1, 1. Now let's eliminate like we did before. So let's take row 1 added to row 2, and then negative row 1 added to row 3. And when we do that, we know row 1 stays the same. Then we'll have 0, and then -1, and then a +1. And then here we'll have 0, 1, and let's see, so that's -2 times 2. Okay, all right, so I think I made an arithmetic error here. So this should be, so we're taking -2 times row 1, adding it to row 3. So that becomes, okay, right, so that's 2 plus 1, so that gives us 3. And then -2 times 2, that's -4, plus 1, that's -3. Right? And then, if I make this pivot a +1, so just take -1 times row 2, that produces this system. And then I think you see what's going to happen when we eliminate the +3, we will also eliminate the -3. So if I take -3 times row 2 added to row 3, oh, -1, and then we end up with 0, 1, -1, and then 0, 0, 0. So there we go. So there's no contradiction. And what this means is, in fact, we can go ahead and solve this and actually write down what the scalars are. So this is telling me that C2 would have to be -1 using my back substitution. So C plus 1 is equal to 2, so that C1 plus 1 is equal to 2, so therefore C1 is 1. And that means So yes. So yes, 1, -1, 2 is in the span of S. And not only can we say that, but we can actually write down what the linear combination is. So if I take 1 times my column 1, so if I take 1 times 2, -1, 1, and then plus -1 times the second column, so that's my C2, times the vector 1, 0, -1, then we will end up with 2 minus 1, that's 1. Then we will have -1 plus 0, that's -1. And then we will have 1 plus 1, and that's 2. And that's exactly what it is. So in this case, we are able to hit our target. Now, what does this mean? Geometrically, well, again, if we start with our two vectors that we know are not scalar multiples of each other, and we generate all possible linear combinations of them, again, we're going to get a plane. Again, I'm just sketching a portion of the plane here. Let me go ahead, kind of shade it in red. So what will happen now is if I take this other vector, our target vector that we are able to meet, the vector 1, -1, 2, and if I draw that vector with its initial point somewhere in the red, that vector stays in the red. So let's say it's here, so it's going to be somewhere like here. If it's over here, maybe here, somewhere like that. It's one of these vectors, right, that is in that plane. It's not pointing out of the plane, but essentially it is what we would say coplanar. So in fact, we can actually introduce that phrase. So another way to interpret this geometrically, these three vectors, so the vectors 2, -1, 1, 1, 0, -1, and 1, -1, 2 are coplanar. In fact, we can say something a little bit more. What that means is I can always write any one of them as a linear combination of the other one, right? In other words, this equation here, it's essentially it's like I took this vector and I kind of isolated it. But I can use my vector algebra and isolate any of these vectors. I could isolate the 2, -1, 1, or I could isolate the 1, 0, -1, all meaning that each one is a linear combination of the other two, right? So again, there's lots of algebra and geometry at play here, and hopefully you found it interesting. All right, see you in the next video.